So welcome everyone to today's HAO Colloquium. Today's speaker is Alan Su. He's a third-year graduate student at the Department of Astronomy at Harvard, and he works with John Samara to build instruments for spectropolarimetric measurements of the solar corona. He's also working on tomographic reconstruction of coronal density, temperature, magnetic fields using spectropolarimetric measurements. And today he's going to talk to us about the probabilistic calibration of procedure for the CORSAIR polarimeter. Please take it away.
All right. Hi, everyone. Thanks for joining. And today, I'll be giving a talk on how we plan to calibrate CORSAIR using a probabilistic calibration procedure. So I broke this talk down into 4 parts. The beginning will give a brief introduction on what CORSAIR is, and then I'll go into a little bit of background about spectral polarimetry, and then I'll describe the Bayesian calibration method that we designed. And finally, I'll show some uncertainty propagation methods that we can use to deduce a little bit of science with this calibration procedure. So what is CORSAIR? Well, CORSAIR stands for Coronal Spectral Polarimeter for Airborne Infrared Research, and it is an upcoming balloon mission, and it consists of a coronagraph and a spectral polarimeter in a stratospheric balloon. And we plan to measure corona's magnetic field, temperature, density, and velocity. So we'll be doing a 1-day test flight, I think this fall in New Mexico. And then in 2028, we'll do another 1-day test. And then the actual flight will be a 1-month science flight in Antarctica, where we'll be observing the sun for a full solar rotation in an attempt to try to understand the global magnetic fields over extended periods of time. Okay. And here I've just shown some pictures. They're not the actual CORSAIR balloon, but it's something similar. So this is the Gusto launch, but you can see the balloon is there. And I think here I'm showing the gondola. So we'll put the instrument on something that's similar to that. These are from like other space missions. I think Excalibur is like an X-ray mission for, I think, black holes, and Gusto is like for the interstellar medium. But these are just to show some of the parts that we're probably going to use. And on the bottom here, there's kind of a flight path of Gusto, and you kind of see that even over 2 months, it kind of stays around the Antarctic region. So it'll be a pretty stationary area. At least that's what we plan for CORSAIR. A few details about the instrument. So the instrument kind of has 3 parts. The first part is a chronograph with a 30.3 meters objective lens, and then it'll focus onto an occulter. And then the light gets passed through the second block, which is a polarimeter. And there's a collimator, and then it goes through a rotating wave plate, and then followed by a linear polarizer. And then once we extract the polarization data, we feed that through the spectrometer, which has a slip plate, and then final grading, and then into the detector. I think the majority of this talk will be on the polarimeter, but I just wanted to give a big picture on CORSAIR.
You said it's a 20 centimeter aperture.
Sorry?
Coronagraph.
Yeah.
What is the aperture of the coronagraph?
I think it said
At the front?
Yeah,
aperture. Oh, yeah. 30 centimeters, yeah. So just to give a bit of a background on what these images look like. So they're going to look something like that. So you can see these vertical lines across, and that's due to the slip plate. So the reason we pass the light through a slip plate is that we're dispersing the spectral information along one dimension. So you can think of it as like a trade-off. So we want to store the spectral information somehow. So we're going to decrease the resolution of the spatial information along one dimension, right? And then the other dimension, I think the horizontal dimension, stays at the original resolution. The lines that we'll be looking at are in infrared. So in the test flight this fall, we're going to look at Silicon 9, which I highlighted in red over here. Hopefully you can see my cursor. It is relatively a new line. I'm not sure if it's been observed too often. It's 39. I think it's around 3943. And we hope that this will give us a good probe into some of the magnetic field diagnostics talked about in the later slides. The actual science flight will have 5 lines. So the iron, I think 13 doublet, 1074, and I think 1079. And then the helium one, which I think is also around that wavelength, around 1 micron. I forgot. the exact number. And then the silicon 10 and silicon 9. And then you can see from these 5 lines, you can get a lot of diagnostics, right? You can get density, you can get temperature. I believe you can also get velocity. And then we also hope to get some magnetic field, magnetic azimuth, and then also the line of sight field strength that we'll get from the polarimetric. So I've kind of blocking it, but on the
only for us here.
oh, okay, I see. So on the right hand side, I've kind of shown kind of these toy drawings of what polarimetric data looks like, a wavelength resolve. So we parameterize light in terms of Stokes vectors. So these are a set of four numbers. We call them I, Q, U, and V that completely describe the polarization of the light that we measure. So specifically, I is intensity. Q and U are the linear polarization components that kind of arise from the Hanley effect. So you can imagine by the limb, the direction you're observing is like 90 degrees. So you'll have a linear polarization component that's kind of left over because one component that oscillates towards you is like be suppressed. And then before the so linear polarization kind of comes from scattering. So like before light scatters off these vibrations, it'll actually, if there's a magnetic field present, it'll actually rotate these linear polarization components, and we'll actually get a trace of the magnetic field at plane of sky. Stokes V, I think the bottom, this curve is kind of measurement of the Zeeman effect. So if there's a magnetic field present, it can split the atomic levels. And then if you look at the wavelength resolve measurement, if you split 3 of them along line of sight, you'll get one that's slightly red shifted and one that's slightly blue shifted. So you get kind of this hallmark Zeeman effect that's like a shift in the polarization. And I'll kind of show some measurements on that on the next slide. So these are kind of the diagnostics for the magnetic field that I'll be talking about. Okay, so actually spectral polarimetric observations have been regularly measured over the past decade or so. So here I just wanted to show some quick diagrams. So COMP, or I guess UCLUMP, now they've been regularly measuring linear polarization for a while. This is just from one of their 2017 papers. I think it's just showing a pseudo-streamer. So on the left, there's I think just some AIA reference images. On the right, you can kind of see the top is linear polarization magnitude measured by COMP. I think it's normal. I think it might be normalized by the intensity. And at the bottom is the angle. So you can take the arctangent of the Q and the U, the linear polarization components. You'll be able to recover the plane of sky magnetic azimuth or the angle in the plane of sky. So that's linear polarization. Circular polarization is quite tricky to measure, mostly because of it's very sensitive, and it's been quite hard to do until like kind of recently, where DKIS has really been able to get some pretty decent measurements of it with cryoNIRSPs. So like specifically, I took this diagram from one of their recent papers. This is a spectra, IQUV. There's 4 columns, but let's just look at the final column on the right. So that's Stokes V, and if you look really closely, it's pretty noisy, but you can kind of see the hallmark of the Zeeman effect right there. You'll see the switch in the polarization. And if you apply like a weak field approximation and then you fit, so actually it turns out that if you apply this weak field approximation, you can relate the Stokes V measurement to the derivative of the I. So if you remember, if the I is like a peak, the derivative is actually looks very similar to Stokes V, and they're actually related by a scale factor. That scale factor is exactly the magnetic field, the line of sight field strength. Okay. And CORSAIR will kind of try to make a lot of these similar measurements, but we're flying it above the atmosphere, so hopefully we'll get some better results. Okay, so this is kind of a brief background on CORSAIR. And any questions, and a bit about spectral polarimetry. Okay, so before we get into the actual methodology, I wanted to give a little bit background on spectral polarimetry so that we kind of we're on the same page. So measuring the full polarization of light. So how do we actually measure polarization? Well, the polarimeter produces a modulated intensity output that contains information about the incident polarization. So what does this mean? Well, I have this diagram here. So you can imagine our sun on the left-hand side, and the input light is S in, which I've wrote as a vector IQUV. Now, our detector counts photons. So we can really ever only measure I. So you might be wondering, well, how do we measure the Q, U, and V? And that's where the polarimeter comes in. So the polarimeter is designed to jumble up the IQUV that comes in, so that when the observed stokes out, so after the light goes through, you'll see that I've labeled the output light as S out, so that has a different IQU and V. The hope is that this I out that we're able to measure contains information about IQUV that came in. And if we do this cleverly, if we design a modulation scheme, by modulate, I mean an intensity that changes over time. If we design this cleverly, we can actually inject enough information of I in, Q in, V in, U in, and V in into the I out, and so that we can invert the procedure and solve for the best estimate of S in. So that's kind of the motivation for a polarimeter. And there's kind of many designs, ways to do this. For us, you can think of the polarimeter as a wave plate, which retards one of the polarization of light at a specific axis by, like, for example, a quarter wave or a half wave, and finally a linear polarizer. Okay, and we need a way to model this with mathematics. So the way that we'll be approaching this is with vectors and matrices. So you can think of light as a 4x1 vector, right? And when light passes through an optic, you can think of it as a matrix operating on a vector. As a matrix operating on a vector that produces a new vector, right? So with this in mind, I've copied the diagram from the previous slide, but you can see that as S in, this red right here, passes through the waveplane linear polarizer. That's equivalent to multiplying the vector by two matrices, which I call the M linear polarizer M waveplate. And then if you combine the two Mueller matrices, you'll get another 4x4 matrix. That's what we can call as the model of the polarimeter, right? And we're almost there. One more step, and then we'll get the full forward model. But if you recall from the previous slide, we really only care about I out, because that's what the detector can only measure. So we don't really care about Q out, U out, and V out. So if you really think about the forward model, the only thing that matters for the P is the first row of the matrix, right? Because the first row of the matrix, when you multiply by S in, it gives you I out, but the other rows don't matter. So if we want to design a forward model for a bunch of different states, because each of these P's is specific to one waveplate rotation angle, but if we want to modulate the light, we need to change theta. So for a set of n modulation states, we can construct a corresponding modulation matrix M, and this maps the incidence stokes to a set of n output intensities. So what does this correspond to mathematically? Well, we just take the first row of P at different angles and we stack them together. So you can look at this matrix right here. That's a bunch of first rows stacked together. If we multiply that by the S in, we actually get the set of modulated intensities I outs on the other side. And we're going to call this this first matrix the modulation matrix M. S in is what we want to find, right? That's what we don't know. That's the incidence stokes. And I measured is a set of measurements we get from our instrument. So M times S equals I. This is our full forward model. This models the observation of spectral polarimetry measurements. Okay. Now that's not quite the story. That's the forward model, but we need to solve for S in, so we need the inverse model. So the demodulation matrix can be computed from the modulation matrix and is used to invert the intensities into the incidence stokes. So this is the equation I had from the last slide. That's the forward model, right? So we know M, that's our model, the polarimeter. We don't know S in, that's the stokes that we want to measure, the IQUV. And we can measure the I measured. So this is a matrix problem. And to solve for the best S in, we take the pseudo matrix, pseudo inverse of M on both sides. Right. So D is the pseudo matrix, pseudo inverse of M, and it inverts this equation so that we can estimate for S in. So the inverse model is now S in equals the modulation matrix times the data that we collect, which is I measured. And if we really write it out, that's the full equation. So this kind of forward inverse model kind of completely describes the interaction of our instrument with the incident light. Okay. Okay, cool. Any questions on this before we move on to the next part? All right, cool. So now we get to.
But I mean, optical elements of your instrument you need to understand very well for this transformation to be
Yes.
calibrated.
Yes. So that's actually the perfect question that will lead us to the next section. So in real life, that equation will never work, right? Because when we buy a wave plate, it'll almost never be the Mueller matrix that we think it is. And that's exactly why we need to calibrate it. And the next section, the Bayesian calibration, I'll be describing a statistically consistent way to calibrate and solve for the calibration uncertainties so that we can propagate them to downstream science goals. Okay. So, right, the importance of a good calibration. So, a good calibration is necessary to minimize the calibration error, which we can propagate to downstream Stokes and magnetic field estimates. So, as you brought up, a real polarimeter will never be well represented by the ideal Mueller matrix formulation, right? We need to include free parameters to characterize these imperfections. There's many ways to kind of tweak the model. For us, you can think of it as our polarimeter is like a 4x4 matrix, that's ideal, but the real polarimeter might be off by a little bit, right? So we're gonna add like little parameters where we believe there to be imperfections, and these are gonna be physically motivated. So for example, maybe the retardance angle isn't exactly pi/2, maybe it's like pi/2 plus 10 to the negative 3 radians, right? And we need to find that offset. And what I'm gonna describe here is we're gonna actually model those offsets as random variables. And we're going to solve for the distribution, the joint distribution of all the free parameters that are floating around in our model. Okay. And right, and to calibrate, we need to collect data from the polarimeter and solve for these free parameters. Okay. Now, this is done for every single instrument, and in fact, the previous spectral polarimeters like UCOM and DKIST already kind of do something like this. They calibrate and they kind of solve for these free parameters, but it is not in like a statistical Bayesian model. They kind of compute the calibration error maybe downstream or maybe through like some type of other type of models. But here I'm kind of presenting a more, I guess, I believe to be like elegant and consistent and much easier to use downstream. Okay. So calibrating a polarimeter. To calibrate a polarimeter, we need to produce known Stokes inputs and measure modulated intensities to solve our model. So what does this look like? Well, if you look at the right half of the diagram, that's what we had before. We had the polarimeter and then we had the detector, right? But now, if you remember this forward model equation, we want to solve for M, right? We don't know M anymore. M is no longer the ideal thing, so we want to solve for M. So we need to know S in, right? Because there's 3 things in the equation. We need to know at least 2 of them. So we need to know S in, and we need to measure the intensities, and to do so, we need to create known S-ins to put into the polarimeter at the front, right? So that's why there's this extra calibration unit in front. For us, we're going to use a simple linear polarizer and wave plate. It turns out that that's enough, and plus an unpolarized lamp. Turns out that those 3 components are enough to kind of generate any known Stokes input that we want to make. There could be other more complex setups. But now you might be wondering, well, wait a minute. Well, the calibration unit, how do we know that's calibrated? Like, how do you know that the Stokes that you're generating is actually the Stokes that you're saying that you're generating, right? So the answer is like, you don't, right? And that's the hard part. You have to calibrate both of these simultaneously, or else you end up with infinite calibration unit in front, and so on and so forth. So that's actually what UComp does in their calibration technique. They do this type of closed loop optimization where they calibrate both the calibration unit and the polarimeter. So there's parameters floating around in the lamp, there's parameters floating around the calibration unit, and there's parameters floating around the polarimeter. And you have to solve all of them at the same time. But during observation, you kind of only use the polarimeter part. But you still need to solve for the other ones, or else you won't get like consistent S-ins, right? So that's kind of the story of calibrating a polarimeter. And now I kind of want to introduce the this kind of Bayesian formulation to approach calibrating. So calibration and Bayesian inference are actually pretty deeply linked. And the key change here is instead of point estimates for each parameter as old calibration methods have done, like in UComp and DKIST, we compute a joint probability distribution for all the parameters. So instead of a single guess for each parameter, now each parameter is now a distribution. right? So it's a distribution over the possible values. So and we solve for the joint distribution, so it's going to be multi-dimensional. So for example, if there are 6 parameters, the distribution that we solve for is going to be a 6-dimensional distribution. Okay, and how do we do this? Well, you'll see there's three curves going on the right. They're in blue, purple, and red. You can think of the blue as the initial distribution, or what we call the prior. This you can think of as the initial guess for the parameter. And this is kind of consisting of all of our prior beliefs of where we believe the parameter to be initially. Then we collect data. That's the second term here. And that's the adjustment from the calibration data called the likelihood. So that's this pink or red curve over here. And we can construct this likelihood from the data that we collect. Okay. And multiplying these two together, we get our adjusted distribution, which is the calibrated distribution or the posterior. So you can think of this as initial guess for the distribution. We collect data to shift the distribution into something more likely. Okay, just a little caveat. This is kind of a toy distribution. In practice, we almost never have a prior that's this strong. This prior is a normal distribution that's saying, okay, we really believe that the parameter is like right at the center. In practice, unless we have a very strong reason to believe so, we'll never do this. We'll usually have a uniform distribution as a prior or something weaker because we don't want our actual final distribution to be heavily influenced by the prior. The prior is just the initial kind of guess or starting point. Okay. This diagram is just to show this to show the Bayesian idea. Okay, so there's a few statistically technical points that we have to go through when kind of deriving this Bayesian model. And the key point is we need to make a model assumption. There has to be some type of noise assumption on our model. And we go with something that's very typically done when we don't really understand the noise of the full system. And that's to say that the measured intensity, so this I, is normally distributed about the model, the polarimeter Mueller matrix model that we have, M. Okay. And you'll see in this equation, it's just the M that we produce. We add some noise to it, and we believe that will produce I, and we believe that this is a good Bayesian model to adhere by. And if we believe this to be true, we can then compute the likelihood, which is a data collection of intensity and angle tuples. And from there, we can kind of shift the initial guess into the posterior distribution, which is combining the parameter, priors, and likelihood. Now, I kind of skip through a lot of the details here, but I'm happy to elaborate on this further. But what I really want to get to is using this method to calibrate CORSAIR, the actual polarimeter. So the first thing is we shouldn't just use this in the lab because we want to test if it actually works. Right. So let's do it on an actual simulation. Let's do it on a simulation of the CORSAIR polarimeter. And why do we do that? Well, we have the ground truths, right? We can actually set offsets in these parameters that we believe to be important in the lab. We have ground truth numbers. And now we simulate CORSAIR observations. Sorry, not observation, like calibration data. And then we take this data, we feed it into our Bayesian model, and we see if we can reconstruct the data, and we can reconstruct all the free parameters that we believe are important. Okay. So summarize, to test the Bayesian calibration, we collect data from a simulated polarimeter and calibrate for ground truth parameters. I never actually stated what the parameters are until now. And this is actually a quite delicate topic. You know, what parameters should we choose that are important enough for the system? For the experiments I'll show here, I've chosen 6. Just note that, you know, you can do more optimization to choose more. But if you choose too many, a lot of them will have very high covariances with each other. And you might not really get physically interpretable results, right? If you choose like 20, maybe maybe like 4 or 5 of them might be jumbled up, and it might be better to just put them in one, right? So just to highlight the 6 parameters that I think are pretty important. The first 2 are the linear polarization imperfections in the lamp. So the unpolarized lamp right at the beginning of the calibration unit, it's not going to be completely unpolarized. There's going to be some slight linear polarization. So we have these 2 free parameters, dq and du, that we put in there that we're trying to solve for. And these are probabilistic numbers, okay? The other 2, the next 2 are imperfections on the wave plate retardances. There's 2 wave plates in our system. We have the calibration unit wave plate and the polarimeter wave plate. And they both might not have perfect quarter wave plate behavior, right? It might be a little off. So we need to solve for those as well. And finally, I have some alignment offsets. So maybe when we're aligning the polarimeter, we don't exactly align them to where we believe all the axes match up. So there might be some physical wave plate offsets. And here, I think you have to be really careful. You don't want to introduce an offset for every single optical element because they're highly correlated, right? They're part of the same coordinate system. So we just choose 2, which we believe will be enough to characterize the majority of the systematics that kind of float around, right? And you'll kind of see like these numbers, generally when we solve for them, they will be physically meaningful, right? All of these are relatively independent of each other, but they might include some, some distributions that capture some of the stuff that we can't see. But we kind of jumble them up into one of these parameters. Okay.
Why are they highly correlated? I mean, naively, I would think you have 4 optical elements aside from the lamp. So why would the angles be highly correlated?
Right. So just to give a bit of idea, for example, when you rotate, it actually doesn't matter where the final linear polarizer is rotated. Everything can be written relative to the last guy in terms of a coordinate system.
Okay.
And yes, so technically there are 3 degrees of freedom, but we chose 2. We believe 2 is like pretty good. But yes, you can add a 3rd one. But if you add, I think, more degrees of freedom than there are, you'll start to get, kind of jumbled information that you're like, wait, which does this one actually correspond to this one? Does this solution actually correspond to actual offset or not? That's kind of the general idea.
Okay, that actually makes sense. And in the lamp imperfections, I'm assuming if you had a circular polarization, you wouldn't care because it's followed by a linear polarizer. Okay.
Exactly. So a linear polarizer is insensitive. That's a good point. The linear polarizer is insensitive to Stokes V, so it doesn't matter if we model it. The information doesn't get propagated. Yeah. Okay. Any other questions? Great. Okay. So let's actually talk about the calibration. I've broken this up into 2 parts. So the first part is red. So we need to I kind of already talked about most of this, but we need to model the polarimeter. So we define the polarimeter model, step 1. Step 2, we collect data. And this is all done. We don't give any of this information to the calibration. So we model this, using Euler matrices in code. And then what we do is we simulate collecting the data with realistic sources of angle noise, intensity noise, but actually relatively high signal to noise ratio because we're doing this in the lab, so we can actually expose this for a very long time. Okay, so we model all this and then we save the data. I would like to point out that the data consists of, so each data point is the state of the calibration unit on the polarimeter. So you can think of it as 4 angles plus the output intensity. It's kind of like 5 values. Yeah, and you do that like maybe 100, 200 times. So you have a bunch of data samples. The third part is calibrating the polarimeter. This calibration is actually purely numerical. So we define the priors as our initial guess, compute the likelihood, which is the adjustment to the guess from the data. The third part is we sample the posterior of the parameters. Now I say sample because the posterior is a very complex distribution. We could save it, but to use it effectively downstream, what people usually do is do Monte Carlo Markov chain samples, MCMC samples of these complex distributions, and we save those samples instead. So you can think of these samples as like maybe 1,000, 2,000 points of that are highly representative of the distribution, so that when we plot a histogram of these distributions, it effectively it's equal to the posterior or very close to the posterior. Okay, and by discretizing this, now we can pass each sample into downstream pipelines much more easily. Okay. So that's the calibration scheme. And now I'll show some results. So what you're seeing here on the left-hand side is something we call a corner plot. So as I mentioned before, there were 6 parameters. So our distribution is 6-dimensional, but our screen is 2-dimensional. So it's hard to show a 6-dimensional distribution on a 2-dimensional screen. So how do statisticians do that? Well, we just pick all the parameters pairwise, right? And we plot kind of the projection of the distribution onto pairwise parameters. And we do that for all the pairs. So that's why you'll see this half triangle. Okay. So each of these blobs, you'll see there's like kind of 6 going down and then a few going across. There's a few subtleties that I probably won't go into detail, but there's actually a 7th parameter, that's sigma I, that comes from our Bayesian model assumption. But for the purpose of this talk, you can just think there's 6. And what you're seeing here are these projected distributions onto pairwise free parameters. And the red it's kind of hard to see, but the red dashed lines, horizontal, vertical, mark the ground truth. And the whole point is we want the posterior to constrain the ground truth as we add more and more data samples. So I've zoomed in to the top corner plot just so that you guys can see on the right hand side. So the top distribution and the right distribution that's kind of oriented 90 degrees, those are marginal probabilities. So if you integrate out all the other parameters, it's the one-dimensional distribution for that parameter. Okay. And this plot is shown for 5 calibration samples. So we rotate the calibration unit just to 5 samples. And this Bayesian algorithm is kind of already able to cluster near the ground truth. Okay, like right there. And now I'm going to step through more and more samples. Unfortunately, the data axes on each subsequent slide are different, but hopefully the spirit is there as I step through them. So this is 10 samples, 20 samples, 50 samples, and 100 samples. Okay. Now, after 100 samples, the posterior pretty much doesn't change anymore. And it's able to be pretty constrained near the ground truth. So you'll see if you kind of scan through most of the other plots, the ground truth kind of hovers near the 1 sigma or the green shaded area. And that's exactly what we want, right? We want this model to be able to capture the uncertainty of the whole systematics through the whole pipeline. And this is a strong indication that because the posterior is constrained and it's consistent with the ground truth, that it's able to do so. Okay, so this is just a summary of the previous slide, but we summarized the mean and the spread, and all 6 of our estimates agree with ground truth values. So there's six rows each for each row is a parameter. The first column is ground truth. The second column is actually the prior. They're actually all just uniform distributions, but you can ignore that. And P estimate is our estimated posterior center and the spread. Okay, so just a bunch of numbers. but the spread here, that's one thing. I think the 94th percentile spread agrees with the ground truth. That's great. Okay, I guess any questions about this whole idea before we move on?
How do you know the ground truth?
Okay. So the whole point of this was to perform the calibration on a simulated polarimeter where we introduce the ground truth offsets so that we can see if we can recover them.
Okay.
And these ground truths are, I picked them physically motivated. So it's like what we believe could be true for the actual lab. And indeed, the recovered one is like all the ground truths are within, I believe this is the 94th predictive intervals, 94% of the area of the distribution for each marginalized.
Got it.
This seems really good up to the 3rd, 4th decimal point. So what would be the effect of an error like that on just those parameters? Maybe you're gonna get to that.
Yeah. So actually the answer is it's actually very little. It turns out that during observations, you're not limited by calibration error. You're limited by photon noise, right? But we want to prove this analytically and consistently, and this is the one way to do it.
Well, depends. If you integrate very, very long and you beat down the photon noise, this is when this matters. But I was like, well,
okay.
It seems small errors compared to
yes,
okay.
Yes, if you integrate long enough, yes, you can go under this. But it turns out I think for most instruments you don't want your calibration error to be limited. So I'll show I think on the last section when we propagate these uncertainties, we'll show some estimates of how observations that we believe to get have photon noise that is much greater than this. And that's exactly what we want to see at numerically and like statistically consistent conclusion. Right. Okay. Any other comments? Okay, cool. So we just did that for the calibration. So what about the lab, right? Does it work in the lab? Well, so we did a lab prototype for the CORSAIR polarimeter, and we're going to test this calibration algorithm on it. So this is the diagram of the whole pipeline, and I took some off-the-shelf Thor Labs optics and set up this whole pipeline. So you can see we have the lamp source in the front with the filter, calibration unit, polarimeter, and detector. Now, unfortunately, when I did this, we didn't have the actual CORSAIR detector, and we didn't have an infrared light source, so I just used visible light. But hopefully, in spirit, it captures most of what we're trying to test. Okay. A few others. I think one other small point I want to bring up. We do this test, I think, at 670 nanometers, so red light. The calibration unit has a quarter wave plate that at 670. But because CORSAIR has a wave plate that we're going to use at multiple different wavelengths, we don't want to pick one that's like at 670. So we picked one at 630. I believe it's quarter wave plate at 633. So it's a little bit off. So we can actually try to see if we can get something, get a good test on a wave plate that's not operating at its intended wavelength. And for the results, I won't show the corner plot, but I'll show the table. And I've kind of simplified it a lot. I've been showing 2 parameters here. I didn't do it for the full 6 one because there's, I think, a lot of, like, for example, if we add like physical offsets in the prototype, the actual angle precision I had was in the actual CORSAIR one. So we just used 2 of what we believe to be the most important parameters. These are the wave plate retardance angle offsets, and you'll see in the 2 columns we'll have the lab, which is the calibrated posterior, and the theory. Okay, so we don't have ground truth, but we have a good theory of what we believe it should be, the value should be around. And you'll see that for the calibration unit, it's around pi/2. Okay, and the uncertainty, I think 0.05 on 1.579 is pretty good. It agrees with pi/2 what we believe theoretically. Now, I think to interpret the polarimeter results, we have to kind of look at some other sources of some other sources of noise that the calibration error doesn't capture. So you'll see that the calibrated posterior actually gives us a retardance angle of 2.58 with kind of error of 0.05. But in theory, we kind of predict this to be around 2.4. Now, this is kind of where we need to look at the error budget, because this 2.43 we actually had to calculate using Sellmeier coefficients from refractive indices papers that kind of model this the wave plate retardance angle equations. So there are some uncertainties there, and maybe that can explain why the 2.58 is off by 2.43. So right. So before I say that statement, the bottom is kind of a small error budget that we made with 4 sources of uncertainty that we believe to be important. You'll see that there's kind of a lot going on here, but there's 2 major parts. There's the calibration unit uncertainties and then there's the polarimeter uncertainties. Each of them have 2 columns. The left column is kind of the uncertainty in the native space. The right column is the propagated uncertainty into the retardance angle space. So there's the angle setting because I rotated them manually. So there's a native uncertainty of 0.5 degrees, and then you can see that propagate to like 0.006 radians. There's the bender tolerance, and that actually only applies to the calibration unit because we're using that one at its operating wavelength. It doesn't really apply to the polarimeter. And likewise, because the polarimeter is 633 nanometer quarter wave plate, but we're operating at 670, we need to use a Sellmeier model to look at the error, I believe, in the birefringence itself. Okay, and that turns out to be pretty small as well. But it turns out that because we have a finite filter bandwidth of 10 nanometers, we put a filter in front of the light. That actually causes a huge uncertainty in the polarimeter because we use a multi-order wave plate. So a 10 nanometer change in thickness, that's many waves thick. Okay, and that actually introduces a 0.39 radians uncertainty on the retardance angle for the polarimeter. So if we do a total RSS, you'll kind of get a 0.39 dominating for the polarimeter. And if you look at 0.39 and 0.05 and you add them in quadrature, that actually explains the uncertainty here, 2.5 and 2.43. So this 2.43, this theory actually has quite a big uncertainty. That's the end conclusion we got here. So with that in mind, I believe it's quite safe to say that probabilistic calibration procedure recovers a posterior that agrees with the theoretical error budget presented below. Okay, so great. So this is another strong indication that this works in the lab. Okay. Any questions before? Yeah. Any questions before we move on to the final part? How are we doing on time?
Still 15 minutes.
Okay, that's good. Any questions? Yeah.
How many angles did you rotate it to? Since
That's a good point. So for the simulation, we did I believe 200, and for the lab we did 100. So 100 points. And these are randomly sampled states for the polarimeter and the wave plate. I would like to bring up that for UComp, and I'm not sure about DKIS, but at least for UComp, when you calibrate it, you actually calibrate it at the specific modulation sequence. right? Because what you're getting out is the demodulation matrix. Here, we're kind of approaching it from the sense that we're trying to figure out the parameters of the fundamental model. So we actually rotate them to random states because we don't want, maybe some specific modulation sequence is very biased to some aspects of the distribution compared to the others. So we want to sample it randomly. Okay. So yeah, 100. And I'm sure you can get better results with more, but kind of converges.
I have a question on this, the methodology here.
Yeah.
So your parameters are physical parameters, in the sense of it's an error on my lamp or it's an error on the wave plate, etc. And I kind of like that idea because it makes like physical sense to me, but I'm not sure that I, at the end of the day, actually care, right? I just want the final matrix. So is there a way to do this with some sort of machine learning where it's just a black box and you tell it to find X number of parameters and give me the answer?
Yeah, so it's a good point. So I think there's a good trade-off here to think about is how much of your model you want to rely on actual physics that we believe to be true, and how much of the model you want to be modeled by machine learning, maybe with some unknown, that to model all the unknown stuff that maybe your model is wrong. And I haven't really explored using machine learning model in this sense, mainly because when we choose these physical parameters, yes, I agree. Maybe at the end of the day, we don't really want. We just want a good demodulation matrix, right? we don't really care about the actual parameters. But the whole goal is to kind of frame this in a way that's, still we want to balance physical interpretability with like practical usage, right? And somewhere along that fine line, you could probably find a good set of parameters that's enough to capture, most of the systematic biases. Maybe some of the parameters won't have physical interpretation, but I still think it's quite meaningful to, have like, for example, lamp imperfection or waveplate retardance, because I think it does teach us a lot about, the system itself that maybe machine learning model might not be able to. But at the end of the day, like maybe if you have a strong belief that your waveplate is not well modeled by a Mueller matrix, you could for sure model the polarimeter with the neural network instead of, a Mueller matrix. And maybe, maybe future work can be done to combine these two, right? Maybe some hybrid version, maybe some parts of the Mueller matrix, you can use some type of network to optimize, but it's a bit out of scope of of what I do.
Yeah, but Paul's point is well taken. At the end of the day, what you care about is demodulation.
Yes.
And yeah, it's interesting to know where in that, using the physics-based scheme, where in that scheme you might have some more errors than others. But
yeah,
if you can get a more accurate model that has better demodulation and is a black box, then I would take it for operations.
I mean, I go the other way. I mean, how does this compare to calculating the demodulation matrix in the,
that's in 2 slides. Yeah. So, okay. Any other comments? Yeah.
The machine learning also has an extremely high specificity, so it might be very well at demodulating that lamp and not the sun. When you train it like that, that's what
You have to train it on your source. Yeah.
carrying to ground it in some physics, or else you don't know if it's universally applicable or not. The intrinsic problem of those methods.
Any other comments before we move on to the last part? Great. So now that we've kind of talked about this whole calibration and we can, compute this posterior distribution as uncertainties, how do we actually use it, right? And the first point is, with the calibrated posterior, we can estimate the distribution of downstream functions of the parameters. What does that mean? We can estimate distributions of demodulation matrices. We can estimate distributions of Stokes vectors that we recover during observations, and even magnetic fields, right? And in practice, this is done by estimating the posterior, so again, our distribution by MC samples, and then passing each of these samples through the downstream function. And once we pass each of these samples through, we plot a histogram of those samples through the function, and that histogram is the distribution of the downstream value. Okay. And just a bit of terminology, these downstream distributions are called posterior predictive distributions because they predict some type of scientific quantity. And we'll be using this idea to estimate calibration errors on demodulation matrices, Stokes estimates, and magnetic field diagnostics. So uncertainty on demodulation matrix, that's really cool. we can actually get a distribution on every single element in the demodulation matrix. So for example, but this requires us to specify a modulation scheme. So up until now we didn't, but now we will have to. So given a uniform modulation scheme of 8 steps, so from 0 to pi, we can construct a posterior distribution of the demodulation matrix. So what does this mean? We have a demodulation matrix here. If there's 8 steps, so it's going to be 4 rows by 8 columns, right? And if you recall what a demodulation matrix does is it maps modulated intensities. So these are your observations, it's modulated intensities, I out 1 to I out 8. It'll map them back to your input stokes. So this is what you want to recover. And as you can see here, I'm plotting the distribution of every single element here. And this blue curve that I shaded is the 94th predictive interval. And here's a fun, it's actually kind of small, but the red line is the ground truth. The blue line is actually compared to the UComp method, but the red line is the ground truth. So I will give maybe 15 seconds. How many of the red lines lie outside of the shaded region? Out of these 32 samples, can you find any? It's actually kind of hard to see, but give it like a little bit of time. There are some. Hard to see. Anyone? Oh, yeah. Which ones? Or can you?
Second one from the left at the bottom, I think that might be out, but it's hard to tell. It's the end.
Yes, that's one of them. That's one. Yes.
Above it's maybe out too.
This one's around the border. Yeah,
And
this one's in. Yeah.
Third one from the right at the bottom is
Yep.
out.
Yep. This one right here.
The one above it is in actually, so maybe yeah.
Yeah. So
It's a few.
it turns out there's two of them. You have identified both of them. They're both on the final row. There's this one out down here and this one down here. And let's think about it statistically. 2 out of 32. That's 1 out of 16, right? So that's 6%. And I plotted the 94th percent area. So what does this mean? This means that our calibration is capturing the uncertainty extremely well. The predictive interval is telling us 94% of the time we'll get the Miller matrix right in this area. And here, exactly 2 of them are wrong. Well, 2 of them are outside the area. So this kind of statistic way of thinking is very powerful, right? This calibration, the way we formulate this calibration error really tells us a lot about how much we can trust our calibration in the long run. Okay, cool. Just a quick, we're a little low on time, so I won't spend too much time on here. But you can actually compute something called the error matrix, which actually gives us information on the crosstalk, which is really important. The crosstalk tells us how much leakage there are when you do this inversion. So maybe some of the IQU and the V might leak into your V out, and that's really not desirable because V is a very small signal, and you really want very accurate V measurements if you want a magnetic field line of sight estimate downstream. So yeah, I will actually, in the interest of time, I will skip this slide. But I guess one thing to note is that our crosstalk is very small. It is machine learning precision. Sorry, not machine precision for Stokes V. And this is really, you want this to be desirable. You want this to be a desirable result from your calibration scheme. Okay. The final thing I wanted to mention in the last 7 minutes is let's apply this to observations. But unfortunately, CORSAIR isn't built yet, so we're gonna have to synthesize some observations, and let's use this calibrated instrument, and let's look at the calibration error and see how it performs with different sources of like photon noise, for example. Okay, so to test this uncertainty propagation to Stokes estimates, we synthesized some spectropolarimetric measurements from a PSI cube, and actually Maxim Kramer did this for us. So thank you for him. And this is kind of what the measurement looks like. I think it's at a specific keratin rotation, I think like 2283 or something like that. But these are the IQUV simulated using coronal line emission code. And I think I picked a specific pixel to show what the wavelength looks like. So I think on the bottom row, IQUV is the wavelength resolved measurements from a particular pixel up there. I forgot which one. But this is at the silicon 9 wavelength, I think 3935. I think that's the wavelength. Okay, and we're gonna basically observe these things. We're gonna pass this through our calibrated instrument, and then look at how the errors propagate to estimated Stokes. Okay. So what do we do here? Well, here I'm just showing the ground truth again. So it's IQUV. I've integrated them with a reasonable amount of time. So for I think we do 30 seconds. Q and U would do 10 minutes. B is for a whole hour. These are what we expect to do for actual CORSAIR measurements. They're normalized by some values. So the actual number might not be physically meaningful. But what we do now is we have two switches. So the first is we reconstruct the Stokes through the whole pipeline with let me see which one I use. Okay, with photon noise only. So we say we have a perfect calibration. Now let's introduce some photon noise and let's see how well the reconstruction is. And then next we turn off photon noise and we turn on calibration noise. And then now we pass this through again and we see how much error is due to calibration. So what this gives us is two results. One is the contribution from photon noise, and the other is the contribution from photon error, from calibration error. Okay, and that's what I'm showing on the bottom two lines. I decided using an MSE metric, so mean squared error metric for every single pixel, and I put them all on the same color scale. So yellow and orange is pretty high, and purple and blue is very low. The first row is reconstruction results using only photon noise for I, Q, U, and V. The bottom one is only using calibration error. And the key thing here is that based on these integration times, we actually get calibration error that's much lower than photon noise error. And that's exactly what we want to see because that tells us that our calibration is good enough for our expected however long we want to integrate the results. So yeah, so our results are photon noise limited. Cool. And now that we can reconstruct the Stokes, we can actually estimate the plane of sky magnetic azimuth from Q and U from the linear polarization, and we can estimate the line of sight field strength from Stokes V, right, using weak field approximation. So these are pretty good magnetic field diagnostics to further test the propagation of error. And again, here I'm showing three columns. Three rows. 2 columns. The first column is the line of sight field strength. The second column is the magnetic azimuth. The first row is the ground truth. The second row is the reconstruction due to photon noise. The third row is the reconstruction due to calibration noise. And these are the actual reconstruction results, but I didn't show the mean square error. The mean square error is over here. And again, these are on the same color scale. Yellow being the highest, blue being the lowest. Again, you'll see that for each, you should look at them per column. So for each column, you'll see that the photon noise reconstruction results are much, much higher than the calibration error reconstruction results. And this is great. This tells us that we're now not limited by calibration error. We're limited by photon noise error. So this whole Bayesian calibration scheme gives us a very rigorous way to compare downstream error sources due to photon noise versus calibration error. Okay, and I will summarize the past two slides here. So for the MSE, each column, there's actually 2 rows going on here. The first row is IQUV, the second row is the line of sight. There's 3 inner rows for each table. The first row is the calibration error, second row is the photon noise error, and the last row is actually the calibration error over the total error. And that's what I want you to focus on. Basically, you can actually add these two MSEs because they're independent noise sources. And if you take the calibration error and divide by the total error, you'll see that these numbers across the board are very, very small. Okay. I guess one final note, you might be wondering like why is Q and U so high and V is so low? That's just the integration time. We just choose 1 hour for V, and I'm sure if we integrate Q and U for 1 hour, it's much smaller. But okay, and with 2 minutes left, I will go through the summary of everything I talked about. So we present a novel Bayesian model for spectral polarimeters and a corresponding probabilistic calibration algorithm for the CORSAIR polarimeter. We demonstrate the convergence and correctness of the calibration on both simulated models and lab prototypes. And we further show that the calibration algorithm enables us to propagate the calibration error and uncertainties to downstream predictions. And a few comments on future work. So many aspects of both the model and calibration errors, I think Fury brought up in the past hour, can be improved. Additional tests on which parameters to use can increase the accuracy during actual CORSAIR calibration. Right? Comparison to baseline models, I didn't really talk too much about this. From other instruments can also be another metric to quantify how well Bayesian model is. And finally, I think for the synthesizing these measurements and estimating the Stokes and the magnetic field, incorporating the forward model of coronal polarization into the Bayesian model inference itself to address the systematic biases for line of sight generated coronal emission is also really important. I didn't So basically, when I do the line of sight integration to generate the synthetic viewpoints, there's systematic biases in the coronal line emission, right, in the forward model. And I didn't model that in my Bayesian inference. But if we want more accurate, probabilistic analysis, we're gonna have to model that. Okay. And with that, I will leave you guys with a final point. So finally, the ideas presented in this work are largely applicable to other instruments, right? A Bayesian formulation isn't just for a polarimeter. It can be applied to the calibration of other astronomical instruments as well. So I invite you to think about how to formulate your own probabilistic calibration ideas in other astronomical instruments that you're working on. Yeah, under there.
Let's thank Helen.
Now, we have demonstrated this in the laboratory with an optical setup, like you will realize it in the flight instrument. When do you calibrate when you fly?
Right. So the plan is we do 2 calibrations, one right before you fly and one right after. The lab prototype here is a prototype. So the actual calibration we're actually doing right now in the lab. And those will probably, I think we're probably doing there's gonna be adjustments to the pipeline for sure. But short answer is we do once before, once after. That's the plan right now, but that could change.
In Antarctica? You'll do that in Antarctica, the calibrations?
Oh, no, we're doing them. I'm not sure about post-flight. I know pre-flight we're doing the lab, but at simulated temperatures.
Okay, I would strongly recommend you do it on Antarctica.
Okay.
Just before the flight. Because we have seen that to have the instrument for the gondola lifts checked is very, very.
I didn't understand. Is it a single beam or is it a dual beam polarimeter?
Oh, you mean before the spectrometer?
Yeah,
I think it's a dual beam.
before the spectrograph.
Sorry,
Yeah,
I'll go
maybe
back.
it's on the.
Are you referring to
Yeah, in your opticals.
that right there? This part? Or
Right. So you have the slit plate is there.
Yeah.
Um,
are you asking if it's going like there's something else here, or if that's
What he's asking is, are you analyzing 2 orthogonal directions of polarization simultaneously or only a single direction? So what's the analyzing element in your polar?
Oh, it's just a single linear polarizer analyzer.
Okay.
Yeah. So maybe single beam.
So
Okay. Sorry. Didn't know the terminology. Yeah.
Oh, and I was wondering why you only want to fly 20 days or 20 plus days?
I think
Because, I mean, NASA's bragging they can now fly 57 days.
get one of their giant balloons. So
it's a good question. I think maybe it's
different. It's a much different balloon, I think.
not sure.
That long duration. So
Maybe the balloon could, but I'm not entirely sure about the logistics. Maybe you have to sign up for something beforehand, and then if it gets delayed, it's
But you're flying with NASA.
Yeah.
And again, they can do 57.
I'll bring it up.
Depends on how heavy your total payload will be.
Not sure about the total weight.
Any other questions?
have you
There are other components that are crucial to such an observation that are not intrinsic in your model like now. And I'm thinking about the wavelength range and the detector. And probably, as you say, there's a high covariance between them. So I think you do need to include your detector performance in such an estimation, because it will be one of the crucial steps. And even when your producers will say they're going to sell you a cadmium telluride that works at both 1 and 4 microns, you should interpret that statement as it works at both 1 and 4 microns, but it won't work in a similar way. Its performance will be wildly different. And for the polarization, that matters a lot. I think the detector wasn't, and the end of the beam wasn't captured in this. And I think it might introduce a huge amount of error in practice. So I think it should be considered that you include such this type of estimation in your model to be able to use it in practice.
So basically you calibrate as a function of wavelength. It's like
And the function of some
some
physically meaning parameters, not actual fixed parameters. A function that combines detector performance with performance at X wavelength. Because everything is really nicely behaved on a silicon detector at 600 nanometers. Things start to go wacky at 1 micron with the standard in gas, and things are very weird at 4 microns with the cadmium telluride. And I think you need to account for these things in such a setup to be able to actually run a good model in practice. Or else you might want to consider them separate things, and you say you're calibrating strictly the polarimeter here, and then you have another calibration stack for your detector and image. But then it's complicated to take them separate. I don't
Ideally,
know which is better, to take them separate or to try to combine them in one calibration stack.
no, ideally you want an end-to-end instrument calibration.
Yeah.
But it's very risky to do piecewise. Maybe sometimes you can't, so you have to do piecewise.
Any questions online?
I forgot to say this is a great data. I really enjoyed it. And congratulations for this work.
Thank you.
I should have started with that. It's very nice.
Yeah, I came in late, I'm sorry, I didn't hear when the flight date is.
So yeah, we have a 1 day like test flight this fall in New Mexico, and then I think one more in 2028. Between then and now and then we're gonna fix up some stuff, and then the actual science flights in 2030. It's fall. They're all fall.
When is this?
2030.
2030.
Yeah.
Balloon was supposed to be faster than that.
That's almost like
Spacecraft. This was the
Yeah. Get a SMEX and
Good luck.
If there are no more questions, let's thank the speaker again. Thank you everyone for joining.